Hello. I think you should be able to see the desktop and hear me. Okay, great. Let me keep popping up windows. Okay. A lot of people still haven't arrived yet. Okay. Okay. All right. Okay. Okay. Um, I've got a reading assignment. We're going to start next week, another render. Let me download some stuff. Okay. And let me just show you real quick. Okay. The new render, it has the advantage that it finally lets us do transformations. So can now rotate things. Okay. So now we finally have the ability to rotate things. Okay. So that, and there's more to it than that, but like now the translations are no longer being done by adding to a vertex, adding to X, Y, and Z. They're now being done by matrices. And since we have matrices, we can do things like rotation. It works a lot. So anything can be rotated now in X, Y, and Z direction. Okay. So that's the main. So it's a render that lets us use matrices, but that opens up a lot of stuff. I mean, it's one of the biggest parts of all of computer science is the use of matrices to manipulate models. Okay. And then the next step after that is we'll be able to use matrices to move the camera around. Once we have matrices built into the, like right now, we can't move the camera. So that'll be a next step is that once we've introduced matrices that lets us do things like this with models, then we can actually use the matrices also to move the camera around. Okay. So what you need to know for that, there's a couple readings. This is an old document. It was written a long time ago, but I actually think it's kind of nice. I want you to read the first 19 pages of it. And darn, got a weird way of being stored on the internet. See, sometimes you click on it and it works, and sometimes you don't. I gave 2 links to it. The document, it was written a long time ago. It's up on a couple different websites, and like this website just acts weird. Sometimes when you click on it, you get the document itself. Sometimes it downloads the document. Okay. But here it is. I mean, either link should work. One of the 2 links should work. Okay. It was written a long time ago, but it's got a real nice explanation of matrices. So first it explains matrices in the plane, like how do you do translation? There's the formula. Okay. How do you do scaling? There's the formula. Now, first it does it without matrices. So here's the scaling formula. Scaling means make things get bigger and smaller. Okay. And you can scale. Here's a distortion. Scaling is what does the distortion we've been talking about. When you do asymmetric scaling, that's actually where the distortion comes from. Okay. So that's these formulas where you have a different S and X and Y. Okay. So he shows pictures to explain that. And then here's rotation. Okay, there's the formulas. Then after he's gone through and done all of them with formulas, then he says, okay, now let's do them with matrices. We can encode the formulas into matrices. I think that's a real nice way to do it. First, just show you that they're actually, you're just working with simple formulas, like, middle school, literally middle school mathematics formulas. They're all y equals mx plus b, because these are linear transformations. So every formula is just y equals mx plus b, but then those formulas can be encoded into matrices. And he does a nice job of then going through and showing you how to encode each of the translation, scale, rotation, shear into matrices, okay? And then talk about multiplying matrices, okay? And order is important. Explain something we're going to talk about a lot, homogeneous coordinates, okay? And then after they've done all this in 2D, which you can draw nice pictures of, it switches to 3D, okay? And gives you the same idea in 3D. Now here they go straight to the matrices. They don't need to go through the they don't need to really do the formulas over again. So they just go, they give you the matrices for scaling, rotation, and shearing, okay? And there, see, there's the reading ends there, page 19. I said to read up to page 19. So you don't need to read about perspective. If you want to, you can read what he has to say about perspective transformations. But there's a way to do the perspective projection using a matrix, but we're not going to talk about that for a while yet. So those 19 pages do a really nice job of explaining this. And then I found another website that actually also did a kind of a nice job explaining these things. So geometry and transformations. Another explanation of the similar idea, kind of nicely written, okay? This is from Estonia, okay? This of all places, this was written by somebody in Estonia. The University of Tartu, okay? The University of Tartu is in Estonia, okay? And they made it, they created actually a pretty nice website. All these things here are pretty well written. They're a nice overview of computer graphics here. You know, actually pretty good, simple, nice overview of computer graphics with little demos. See, little Three.js demos built in. He wrote some little demos and built into the explanation. So I kind of like this site. But these three introduce transformations. Geometry, which we've talked about, but see, he reviews coordinate systems, and he reviews points and vectors. So if you want to understand his way of using words, it may be a good idea to just start with his introduction. Okay, so it's like 2 pages long. But yeah, and then he also introduces this idea of homogeneous coordinates. Okay, but the thing of that's about just geometry in general. Then these two are about transformations. Okay, the second one does rotations and translations. Okay, all right. So two readings, this one and this one. Okay, this one's an older one. Let me show you real quick something here. Show you give you how old it is. If you try to read it, it doesn't really work. Like when you get to chapter 3, see these words? Those are graphics libraries that predate OpenGL. Yeah, you still see references to them occasionally. Nobody uses them anymore, but that's how old this is. This thing predates OpenGL. Those were the graphics libraries that people used before OpenGL existed. Okay, so and actually OpenGL was written in the early 90s. So this was probably one of the last things written that still referred to these older systems. When this was written by 1995, a lot of people were using OpenGL. I think OpenGL came out in 92 or something like that. 1990, 92. But that's how old this is. It's referring to you probably don't want to read this chapter because it's just really hopelessly out of date code. But okay, but the first 2 chapters, well, up to page 19, really nice explanation of matrices. Okay, so that's what we're going to talk about next week. Okay. And again, it's going to allow us to do some pretty fancy things with rotations and transformations. And then we'll also, another thing we're going to be able to do is sophisticated models like robot arms and solar systems where you have things inside of things. You know, we've never put things inside of things. Like a robot arm has got, you can move it at a shoulder, you can move it at an elbow. If you think about it, there's actually some it's not obvious how a robot arm would move at a shoulder and make the rest of the arm move with it when the other parts of the arm move independent of the shoulder. So one of the really important things that matrices give us is the ability to build objects that are compound objects, something called hierarchical objects. Like in the classic examples are robot arms, solar system with a planet going around a sun and a moon going around a planet and a satellite going around the moon. Okay, we can solve really interesting complex graphics problems once we have matrices. Okay, so that's there's the reading, and if you want to play with the render, you can download it if you want to play around with it. Oh, let me show you one thing. Uh, that's a puzzle we'll do. Like we can do things like that. Notice how I'm making a P walk down the line and grow at the same time. Funny little animations like that are things that we can do. And that's one of the things our goal is to be able to like that's actually that's not a trivial little thing to do. Yeah, so we'll learn how to do cute little things like that. There's a whole bunch of examples in here of cute little things that we want to. Here's another one. Just walk the P down. Okay, that's what our goal is, to learn how to solve little animation puzzles like these. So this folder is actually full of little animation puzzles, and they're all solved in here. So each puzzle is a little animation, and then here's how to solve it. The code is right there with it. So you get a little puzzle, a video of the puzzle, and then code of how to solve it. Okay, and that's what we're going to be talking about, is like what can we now do to do these kinds of things. Okay, all right. So okay, that's what's coming up. Preview of future. What's the right word? Preview of future attractions or something like that. Okay, now want to finish talking about aspect ratios. Okay, oh, let me show you. We looked at these demos in here, and these demos actually emphasized more pictures and 2D stuff than the view volume. You know, there wasn't much mention in this folder of view volumes. It was really much more aspect ratios. Okay, so it wasn't talking about the camera and the view volume. Now, if you go down here, I can show you examples of how the camera can make use of this. What can we do now? Okay, so here's a scene. Okay, and you can change the model in the scene. If you don't like looking at cows, you can look at other models in the scene. Okay, here's the ship. Notice that there's an airplane sitting off here. The airplane, I put it there on purpose. The airplane's partially off the scene. Now, before, we had no way of making the scene larger. You couldn't widen the view of the camera and see the airplane. So that airplane's been there in all the previous versions of this program. But now, because we can control the camera, we can widen the view of the camera and we can see that airplane sitting there. Okay, now over here are some new controls. Okay, let's see which one we want. See, O for change the size of the camera's view rectangle. Okay, now what that does is, oh, let me make give you a sense of a picture of what we're doing here. Okay, remember, you have, here's the view plane in front of the view rectangle, and you can control left, right. Now notice that that's enlarging the camera volume. See, so you're enlarging the camera volume. That's what we can do over here now. We don't get this nice pretty picture of it, but we now have a way over in this program of doing that. See how as I open up the camera, I see more of the scene or less of the scene. So opening up the camera can let me see more or less of the scene. Okay, so over here, the O key, well, there I'm narrowing the camera and I'm zooming in on the ship. And here I'm opening the camera, and now I can see the airplane. Okay. Now it looks like I'm making the scene move away from me, but I'm not actually making the scene move away. What I'm changing is the camera, and you kind of get the sense of that over here. it doesn't, it's not so obvious here, but you know, as you do this, sometimes it makes it makes it kind of look like it's moving away from you. See, as I make the camera, it kind of looks a little bit like the thing's moving away from me. Whoops, it's a little bit harder to control this one. Okay, because it got smaller. But why did it get smaller? Because it fills up less of the view volume. The object's not moving away from the camera, but it's getting smaller because it just occupies less of the view volume. Okay, so that's what I'm doing over here. I'm making the view volume just get wider and narrower. Here it's getting narrower and zooming in. Here it's getting wider and zooming out, but the camera is not moving away from the ship. Now, here I'm zooming in on the ship, okay, by using the camera. Here I'm making the ship get close, but see the difference? If you didn't have the background, you couldn't tell the difference between this and this. See, without the background, they would look the same. The ship just gets bigger. Okay, but here I can tell that I'm moving the ship. What's the obvious answer? How do I know I'm moving the ship, not changing the camera?
The background is staying still.
Yeah, the background stays still. So that's the signal that I'm moving the ship, not the camera. And this is moving well, it's not moving the camera, it's changing the aspect ratio, the view volume of the camera, but it changes everything the camera sees. So you get a signal that's changing the camera, not the ship. Like, here's another thing I can do that's actually a little bit tricky. Okay. Right now, okay. Right now I'm moving the ship. Right now, oh, I'm sorry, I can't do that. Right now, I can't scale the ship bigger. In the next render, we'll actually be able to scale this. We'll be able to do three things. We can change the shape of the camera. To make the ship look bigger, there's three things you can do. Change the shape of the camera, make the ship get closer to your camera, or make the ship grow. But we can't make the ship grow yet. It doesn't work in this render because we're not using matrices yet. So I actually can't make the ship grow unless I switch to orthographic projection. In orthographic projection, now I can make the ship grow and shrink. But now as you move the ship closer and farther, you don't see any difference. So it's kind of a quirky renderer. Because we're not using matrices, scaling doesn't quite work right. Okay, so I can't, but there's three ways to make the ship appear larger. Make it closer to the camera, make it grow, and make the camera's view volume change shape. Okay, and without a background, you can't tell which one of those you're doing. But with a background, you can tell which one you're doing. Okay, okay. Now, notice that there's no distortion here. You know, I'm zooming in and out, but nothing's being distorted. Okay. Here's another way to zoom in and out. I'm using the N key. This is another way to zoom in and out. I could either use the O key and I can use the N key. In this picture over here, the difference is the O key moves this left, right, bottom, top. Okay. The N key moves this near plane. It keeps left, right, bottom, top. Now see, watch. See, as I move the near plane, see the shape changes also that way. See how there's two ways for me to change the shape of the view volume. I can move the near plane, but keep the left, right, top, and bottom the same place. Or I can move left, right, top, and bottom. Now over here in the render, the moving the near key is the N key. The N key moves the near plane. The O key changes left, right, top, and bottom simultaneously. Instead of having all these different keys over here, the O key, I think of it as like opening up the render, opening up the view volume. It moves the left, right, bottom, and top simultaneously. It just moves them in unison. So it keeps the shape, the aspect ratio fixed. So when you use the O key over here, you're growing or shrinking all four of those, left, right, top, and bottom simultaneously. When you use the N key, you're moving the near plane, which does not change left, right, top, and bottom. But as you can see over here, changing the near plane does move just change the shape of the volume. Okay. All right. Now, what about changing the aspect ratio? Notice, in the way over here, if you change left by itself, you're changing the aspect ratio. If you change right by itself, you're changing the aspect ratio. Okay. If you want, so by manipulating left, right, top, and bottom, you can get any aspect ratio you want. See, there's landscape mode, and there's portrait mode. But I have to change left, right, bottom, top to get that. Over here, I just have a key for the aspect ratio. So there is the A key. No, let's see, where is it? You start running out of letters, and I forget which ones I use. R key to change the aspect ratio of the view rectangle. So R. Of course, R for aspect ratio. R for ratio is what I picked. R for ratio because A was already picked for anti-aliasing. Okay. One possibility is I could turn this into a big GUI with lots of buttons and sliders. And the trouble, does anybody have a feel for why I don't do that? Okay. I could, instead of having keys, I could create like a panel over here with all kinds of buttons and sliders. Does anybody have if you've gotten a sense yet why I wouldn't want to really do that? Someday I'll do it, but yeah, I don't know if it's really such a good idea. Does anybody have a good feel? You've done some GUI programming. You've played around with a little bit. That would be a lot of event handlers. What would be the disadvantage of having a GUI over here? I mean, it would be nicer for the user. No, I'm not thinking that it would be hard to navigate. I could design the GUI like that. It would be like theirs. It would look a lot like this guy's here. A few sliders with labels. It could make it. I could just mimic his GUI here. I mean, that's not bad looking. 1, 2, 3, 4, 5, 6 sliders. Okay.
You have to do it with multiple threads.
Pardon me?
You have to do it with multiple threads.
No. GUI programming is single threaded. That's actually one of the rules of GUI programming. Remember, we had to launch our. Remember in the code I explained to you had to launch the GUI code in the event dispatch thread. You have to use the one thread. All GUI programming is done in the event dispatch thread. So it's not a threading issue. That's actually a real common misconception. A lot of books imply that, you can make your GUI code better by multi-threading it, and that's actually false. You do not multi-thread GUI programming. It causes more problems than it solves. So all the GUI programming is in the event dispatch thread. What would be another reason why I wouldn't want to create this kind of a GUI for this guy here? Here's the code right now. Here's the event handling code right now. This is the code that handles every one of the letters. D. See, there's all the letters. Okay, F. What does M do? What does C do? What does E do? What does capital E do? What does lowercase m do? Okay. What would that code look like if I had a bunch of sliders and panels?
It would be a mess.
It would be a royal mess. Instead of you having one place to look where you could say, what does the S key do? And you just look down through for the S key. This actually focuses all the logic in one place. If I made it sliders, believe me, the logic would be scattered. And this is one of the big problems with GUI programming. the logic would be scattered all over the place, and people jump through hoops to try to make that not a problem, because every slider would have its own event handler. So, for example, the N key would have one event handler. The O key would have, well, the N slider would have one event handler. The O key would have another event handler. They might be in separate classes even. This might be another event handler. It might even be a separate class. They'd be a different kind of event. One would be an action event. One would be an item event. One would be a slider event. And then you want to like see what these things do, and you go look for them in the code. And instead of there being 400 lines of code, there's over 1,000 lines of code, and what you're looking for is buried somewhere in there. By keeping the GUI simple as keyboard shortcuts, that focuses all the logic in one event handler. It is simply the key type event handler, handles everything, and then you have a dictionary of all the things that are done. And it actually makes for very readable, very understandable code. Doesn't make for a great GUI, doesn't make the world's greatest GUI, but it makes the code comprehensible, which is my goal. My goal is to make the code comprehensible. So I think I should build the complicated GUI. I should mimic their GUI, if nothing else, to show you how crazy it would get to mimic this with all kinds of different event handlers, and how the logic would get scattered all over the place. As it is now, all the logic, it's one big long event handler. It starts there. There's all the keys. So each keystroke is an else if clause. And then after you've handled every key, there's a little, well, then I just call a method to do some cleaning up. Okay. So after you handle every key, then you call this method that does the setup viewing, that handles what was that essentially takes care of all the things that were changed. So this code records all the changing, and then you go to setup viewing. I forget where that is. Oh, it's down here. Setup viewing, and then that makes use of all the changes, and that's about a paragraph, about half a page of code. Instead of everything being scattered in lots of event handlers of different types of event handlers, it's all in pretty much one place. Okay, so that's actually why I've avoided using a super fancy GUI. Like, now he's not showing you his source code. He just wrote a nice demo. So he doesn't actually, if you want, you can download his source code. He does make it available, but his emphasis is not the source code. His emphasis is a nice GUI so you could play around with it. Over here, actually, the emphasis is on the source code. Yeah, I want you to read the source code so that you can actually see how things happen. Okay, now over here, I can change the aspect ratio with the R key. Oh, my program's become unresponsive. I'm not sure why. Let me close it. Okay, we start it again. Nope, wrong one. Okay, now the R key changes the aspect ratio. Okay, now what mode am I in? Now you see a square window because there's distortion, but if you go back over to this is a little bit tricky question. Do I have my, this is what the viewport is square, but the image rectangle is not square. Is the image rectangle in landscape mode or portrait mode? Think about this picture. Is it in landscape mode or portrait mode? Is this one over here in portrait mode, so it's tall and narrow, or is it in landscape mode?
Portrait,
Why?
because it's vertical. It's tall instead of wide.
Well, okay, so right now, this one on the left is portrait, right? What do you do to portrait mode to fit it in a square? What do you do to portrait mode to make it fit in a square?
You crop it.
No,
No.
no cropping. How do you fit this guy into this guy? This is a square. Now you're right, the answer is portrait mode, but why does that give you this picture? Now think, what do you do to that rectangle to make it fit in this square? Suppose this was made of rubber and you had to fit it in this square. How do you get, see this thing's tall and narrow. How do you make this guy into a square?
You have to like squish it, like. make
You
it-
could, okay, say again?
You have to scale it down.
Scale it down, yeah. In which direction though?
In the Y direction.
Okay, in the vertical direction, you could squish it down, right? You could take
Right.
this top edge and squish it down. What does that do to the cow?
It distorts it.
But yeah, but look at how's he been distorted? What? Yeah, he's been squished down. Now go back over here. There's another way to make this into a square. There's two ways to take this rectangle and use it. Think of it as in rubber. And there's two ways to make it into a square.
You can stretch the Y-axis. You can stretch it long ways.
Which axis?
X.
The x-axis. Yeah, you could either stretch it on the x-axis, which is what this cow's. See, another way to think of it, this cow's either been stretched from his nose to his tail. He's been stretched from nose to tail. That would take this and stretch it to the right. Or you can think of it as being compressed from top to bottom. So there's two ways to get that portrait mode into a square. Squish the top or stretch the side. So this guy is in portrait mode. Now I can find that out by turning on letterboxing. So there's an L key to turn on letterboxing. Okay, so turn on letterboxing, and I see that, oh, he really was in portrait mode. See, if I turn off letterboxing, then that has to distort. But if I turn on letterboxing, then it now makes it puts this into the right shape, but doesn't use part. So it's now using a viewport that has the right aspect ratio, and it's leaving some unused space in the frame buffer. Okay. See here, now I made the camera real wide. Okay, so now I've made the camera what in the left side would look like this. I made the camera like that. See, the camera is now in landscape mode. If I turn off the letterboxing, see, now he's squished that way. Because what do you do to make this thing into a square? You would either squish it horizontally, and over here you see the cow's been squished. He's been squished from tail to nose. Or you could also make this a square by stretching the top and bottom away, and this cow has been also stretched vertically. Okay, there's what he looks like with letterboxing. So that's preserving aspect ratio, and here's what it looks like when it gets distorted. Okay, so now I have the ability to do all this over here. I can do what this picture shows you very elegantly. You know, I can change the shape of this view rectangle and this view volume. Over here, you have to kind of imagine what it's doing. You know, there isn't this kind of display here, but with the keystrokes, with the keystrokes here, you can change all the things that this thing can change. But you have to read, you have to, but you have to read what this thing says, and also you may have to read the code, to actually get a sense of how this O key works. Well, actually, look at the code. Like, what does the O key do? The O key over here, the O key changes the left, right, bottom, top. What it's really doing is changing the left, right, bottom, top. That's not obvious by doing this. I'm hitting capital O, lowercase o. I mean, it's over here. It just says O for change the size of the camera's view rectangle. So go look in the code, look up O. See, here's the O key, lowercase o and uppercase O, and you see that it's left, right, bottom, top, left, right, bottom, top. Lowercase o moves left to the right and moves right to the left. And it moves bottom up and it moves top down. So what is that doing to the view volume? Move left to the right, move right to the left, move bottom up, move top down. Think about that over here. So what does lowercase o do? Shrinking it. Shrinking what? The view volume. Yeah, shrink. It's lowercase o's shrink, but it's simultaneously moving left this way, moving right that way, moving top down, and moving bottom up. So it's shrinking. Instead of you having to move all four of these, it just moves them all four together. So it keeps them all moving together. And then uppercase O, moves left to the left, moves right to the right, moves bottom down, and moves top up. So it grows the view volume. Okay. And it keeps the aspect ratio proper. So what that does is if the rectangle looks like this and you want to move this out, you have to move him out that keeps the aspect ratio equivalent. If you move him to the right, by the time you move this one up, you won't preserve the aspect ratio. For example, if the aspect ratio is 2 to 1, this guy should move out twice as much as this one moves up. Okay? So you have to move the left and right by an amount proportional to the aspect ratio to preserve the aspect ratio. So these formulas are a little bit tricky. Here, he does not preserve the aspect ratio. So when he moves left, the aspect ratio is changing. See, the aspect ratio is changing. Here, I moved left in a way where it preserves the aspect ratio. So here, I'm keeping the aspect ratio constant when you use the O key. Okay, and he could have done that here if he wanted to. Instead of having a left, right, bottom, top key slider, he could have just had one slider that just made this thing larger and smaller. Okay, so he did it with four. Now the four sliders are kind of nice because it lets you do independent. Like, what does it mean to move left? What happens if you move just right? You don't do this very often in computer graphics. It's pretty weird to have a view volume like that. That's a pretty weird view volume. The camera's staring straight ahead and the view volume's off to the side. You would almost never do that in a real game or anything. The camera's not looking into that view volume. The camera's staring straight ahead, and it's like a person with two eyes who covers up one eye. It's sort of like the camera's like covered up half of its view volume. So it only sees the part off to the right. It's not looking down into that view volume. This is a real tricky. A lot of people confuse what this thing's doing. It's not looking down the view volume. It's looking straight ahead. And then out of its peripheral vision, it sees a little bit of what's inside that view volume. So this is the peripheral vision. That's all it sees. It only sees its peripheral vision. Okay? You barely do this kind of thing. In a game, I don't think there's ever any reason why you would set up a camera this way, so where the camera's staring, unless you're trying to create a sense of, you're trying to give a character a weird sense of tunnel vision. The camera's staring straight ahead, and it's only seeing part of its peripheral vision. Okay. Now, it's a different issue is turning the camera to look in that direction. You could turn the camera to look down through that view volume, but that's a completely different issue. turning the camera is completely different than changing its view volume. That's a confusing aspect. Changing the view volume keeps the camera looking straight ahead. And when you do weird things like this, it's just strange. Like right now, the camera only has a little corner of peripheral vision off to the right and above. And there's nothing in that little corner of peripheral vision. But the camera is looking straight ahead, and there's this little corner of peripheral vision that it can see. Okay, so this guy lets you control the camera that way, which is kind of neat that you can do it, but you almost never do it. As far as I know, the only thing that people do that's asymmetric is the bottom. It's not unusual to make the bottom flat. There's a certain aspect of photography, I believe, where if you see the bottom extends down like that, if you make the bottom flat, I think it mimics how some kind of cameras work. So I think that the only one of these four that anyone ever makes odd is the bottom one. Okay, because if you think about it, if you hold your camera level and you look out through your camera, see all this stuff? It's below the floor. It's below the ground plane. So you don't actually see any of this view volume. So your camera doesn't actually see anything down there because the floor, you can see there's a little floor plane here. See how the floor plane's cut off right there. So I think sometimes it's common for certain technical reasons to like make this level with the floor, or angle it down towards the floor. So I think that gives you in some situations, a more realistic sense of how the camera is working. Okay, left and right are almost always symmetric. The left and the right are almost always going to be symmetric. And the top is almost always going to be like that also. But I think it's the bottom that people play with. I think there's a certain situation where they would make it level. Okay. All right. So now over here, I didn't give individual controls to left, right, bottom, top. Okay. But the aspect ratio can be controlled. The near and far, the near plane can be controlled, and the size of the view volume can be controlled. Okay. All right. So you can play around with the camera controls in all of these examples now. And so, for example, you can zoom in on this thing. Now I'm zooming in on it, as opposed to moving it. Now, actually, see, notice there's moving it in and out. I'm making it farther and near, and here's making it zooming and zooming in and out. Oh, let me show you one last thing. If you want to know what where the camera is, use the M key, and it'll tell you where the camera. Well, no, M key for the lowercase m tells you where the model is. Uppercase M tells you what the camera is. So for example, I'm changing the camera. I'm changing the near plane right now. See, look at this number here. I'm using the N key to change the near plane. Okay. So you can ask the renderer to tell you, if you go to the help, it'll tell you that the M key toggles showing the camera data. Okay. And the lowercase m key toggles displaying the transformation. Where is this guy in terms of X and Y coordinates? So now you can see how he's moving left and right. In the next render, this will be a matrix. In the next render, instead of showing you how much the delta is that this thing is moved left and right, this display will show you the matrix that's moving this thing. So in the next render, the lowercase m key will display a matrix. That's actually why I made it. That's why I was using the letter M here. The letter M is going to mean matrix. Show me the matrix of the transformation. Okay. All right. So you can also watch things happen here. Like if you think about it over here, you see the numbers here. When you do this, he shows you the numbers right here. Okay. And over here, when you make your changes, I show you the numbers. If you turn on the capital M, I show you the numbers over here, left, right, bottom, top, near. Okay, so the numbers are shown over here if you turn on the M key, and if you then you can turn it off and see now I've got the display turned off, and you can turn it back on again, and there's the display turned on. So the renderer can give you all kinds of feedback, and it's all text based, yeah. But it's remember it's text based, not GUI based, so that when you go look at the code is comprehensible. If I made it really GUI based, it would be fun to play with, but then the code would just become so much harder to read. Believe me, the GUI code is pretty messy to read. Okay, all right. So now, one last thing to do with this is we never looked at what does the render do to create the, I shouldn't have closed that one program. What does the renderer do what does the renderer do to allow this? What does the renderer do to make that volume change shape? How does that work? What is, what code is in the renderer? Okay. All right. Now, it's 10 lines of code that take a lot of explaining. So let me show you the code first. In the pipeline, let me do something. Let me delete the class files that we built. Makes it easier to read the code. Okay. Okay, in the pipeline, there's a new stage in the pipeline. Okay. Let me build the Java docs so you can follow along in the Java doc. If you look at this README, it tells you that what we're doing is we're adding a new stage at the beginning of the pipeline. Okay, so what the README explains is this is all done by a new pipeline stage that comes before projection. It's called the view to camera transformation. Okay, what it does is it changes our point of view from what we call view coordinates to camera coordinates. Now, camera coordinates are what notice that this says view coordinates and this says camera coordinates. The earlier renderer started in camera coordinates. Okay, in the earlier render, you started with camera coordinates. Now, by camera coordinates, I meant the coordinate system in R3, where the camera is sitting at the origin, staring down the negative z-axis, and its view volume is the view volume that goes from -1 to 1, left and right, and from -1 to 1 from bottom to top. Okay, so we call that the standard view volume. That's camera coordinates. Okay, view coordinates are three-dimensional space relative to the arbitrary view volume. So view coordinates is this space here. This is view coordinates, this space here, where the view volume has any shape we want. Okay, so that gives all these points coordinates in this 3D space. Now, what we want to do is we want to take this view volume and scrunch it into the standard view volume. That's what this transformation does. Now, why do we want to do that? Because our clipping algorithm knows how to clip in the standard view volume. Okay, so what we don't want to do is clip to this view volume. Okay, we could not have this new transformation, and we could write our render to just rewrite clipping so that now clipping changed what it clipped against. If you change this view volume, then clipping would change which edges it's clipping on. Okay, so as this shape changed, the clipping would have to change. See, now you'd clip on that rectangle. Now you'd clip on that rectangle. Okay, but that's a big pain. It is not a good idea to make the clipping algorithm depend on all these numbers here. Okay, that makes the clipping algorithm slow. It slows it down, and also why would we want to rewrite the clipping algorithm once it's working? Okay, so we take the point of view that we like our clipping algorithm clipping on the standard view volume. So what we'll do is we'll start with an arbitrary view volume, and we'll take the arbitrary view volume and scrunch it into the standard view volume. So another way to put this is, over here we're in an arbitrary, and then this transformation transforms us to the standard. We call it the standard view volume. Has aspect ratio 1. Its left is -1, its right is +1, its top is +1, its bottom is -1, and the aspect ratio is 1. Okay, that's the standard view volume. That's the one we've been using. Coordinates relative to the standard view volume are called camera coordinates. Coordinates relative to the arbitrary view volume, the one the user chooses, those are called view coordinates. Okay, so there's a view to camera stage in the pipeline. The view to camera stage in the pipeline is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines of code. This one handles the perspective projection, and this one handles the orthographic projection. It's really just 5 lines of code. It really actually is. If you ignore the parallel projection, it's that 5 lines of code. Okay, 3 lines of code here. And actually, I could delete one of the lines of code. This line of code's not doing anything. I just left it in there because I wanted to be kind of mathematically complete. It's literally 4 lines of code. That line of code and that line, those 2 lines of code there. That is this first step. Those 4 lines of code, this is why graphics is such a, to me, an interesting thing. Those 4 lines of code can take you a week to wrap your head around. If you read all the explanation, it takes a while to get sense of what exactly those 4 lines of code are doing. Okay, so what they're doing is transforming from view coordinates to camera coordinates. Another way to put it is they're changing the arbitrary view volume into the standard view volume. Okay, now there's, in here is an explanation. Oh, here's where the formulas are derived. If you read this, there's the derivation of the formulas. So the formulas in the code are right there. See, those are the formulas that are in the code. And then below it is the steps it takes to do the algebra to derive those formulas. Okay, and the derivation is just a couple paragraphs. It's that. That's the derivation. Then this part does the orthographic projection. The more interesting one is the perspective projection. So the explanation is right there. Okay, so it's explaining where these 4 lines of code, how I arrived at those 4 lines of code. And first it explains how to get these 2 lines of code, then explains how to get those 2 lines of code. Okay, now this explains it in, there's the code, there's the explanation written like in a math book, and then I drew some pictures to try to give another explanation of it. So if you open the folder that has the pictures in it, there's that folder called rendering that has pictures in it. Under camera and aspect ratio, here's some view volume pictures. Okay, so let's go through these pictures. Here is a 2D version of a view volume. So it's only showing you the X, Z direction. It's a lot easier to think about this stuff in 2D and then just say, okay, I know what 3D does. Because the third dimension is just coming out at you, and it's just essentially the same picture. Just this is the XZ cross section of the 3D, and the YZ cross section looks the same. But we'll derive the formulas in the plane, and then that makes things a lot easier to do algebraically and draw pictures. Here's an asymmetric view volume. See, the view volume is this heavy black line. So the camera's staring down the Z-axis, and it's got more peripheral vision to the right than it does to the left. That's what this would mean. Yeah, humans don't work that way and cameras don't work that way, but you're allowed to actually program the camera that way if you want. You can give the camera a lopsided sense of peripheral vision, more on the right than on the left. Okay. The near plane is used to determine how far. See, you have this left and right. Oops, you have the left and right coordinates. That over here, that's left and right. So you have the left and the right. I'm not going to do the top and bottom in this picture. I'm only going to do left and right. So you control left, you control right, and you have the near plane. You have the near plane. You go out to the near plane, measure to the right. That's where one edge of the view volume is. You go out to the near plane, measure to the left. That's where the other one. So that's why when you move the near plane, see if you keep left and right fixed, and you move the near plane to there, see how the volume gets narrower. Because now you go out to right, and that's this edge. You go out to left, and that's this edge. So as the near plane gets farther away, the volume gets narrower. See, you can see it on the left. As the near plane gets farther away, the volume's getting narrower. And as the near plane gets closer, the volume's getting wider. Here, there's the near plane getting real close to the camera. You go out to the left and you get this line that's much wider than it was before. You go out to the near plane, over to the R, and you get this. Okay. So moving the near plane changes the width of the view volume. So these are different view volumes. You can either move, now notice that if I want to, I can leave near where it is and just change R. And then that will move this line. That over here would be leaving near where it is and just changing R. Okay, right? So I can either move near and change and keep L and R fixed, or I can change R and keep N and L fixed. Okay, and that's what he lets you do over here. Okay, what we want to do is transform this arbitrary view volume into the standard view volume. Okay, we want to change, let's see, now, if I go through and open these again, Earthframe View will lay them on top of each other. Okay. What I want to do is essentially, see, I want to shift that, see that lopsided view volume, I want to shift it so that it's the standard view volume, which means I kind of have to shift it to the left and then scrunch it to fit in there. Okay, I have to kind of make this view volume that's kind of pointed in the wrong direction. I have to point it in the Z direction and then scrunch it to be a 40, this is a 90 degree, this one's got a 90 degree angle here. That's the standard field of view. So it's got this is a 90 degree field of view. The other one's got an arbitrary field of view. This could be any angle. I want to sort of center this thing and then scrunch it so that it looks straight down the Z-axis. Remember, I said the camera is looking straight down the Z-axis, but I want the center of the field of view to be aligned to the center of the Z-axis. Okay. Now here's another picture that shows that. Okay. Here's that arbitrary view volume. See, there's that arbitrary view volume. The red line is its actual center. Now, the camera's not looking down that center line, but that center line is important to us. We want to do what's called skew the plane so that that center line shifts over to the Z-axis. That's called a skew formula or a skew transformation. Okay, I want to push this. I want to push all the points in this plane to the left so that everything causes this line to shift over. Now notice that, like here, this line shifts over that much. Up here, this point has to shift more. This line has to shift more. This line has to shift less. Here's the formula over here. Here's the shifted coordinate. Here's the original coordinate. That's where I am over here. I want to shift, I'm sorry, that's where I am over here. I want to shift here. The amount I need to shift by depends on how far away I am from the camera. okay? So I'm going to add a shift to x. Now, in fact, I'm going to be shifting left, so these are going to be negative numbers. Here it's written, yeah, this s will turn out to be a negative number. Well, no, actually, no, I'm sorry. The z's are negative numbers. See, this is the negative z-axis, so this is actually a subtraction here. But that's because the z's are negative numbers, so this is really moving me left, okay? Every point on this line needs to be shifted over by a different amount. So as you get farther away, you shift by larger amounts, okay? So this x-coordinate gets shifted over to here. See, the original x-coordinate, the new x-coordinate. The original x-coordinate gets shifted to the new x-coordinate. The closer you are to the camera, you shift by a little bit. Get farther away, shift by a little bit more. As z grows, you shift by more, shift by more, shift by more. So that's the skew transformation. But what's s? How much do we skew by? This point should skew to that point. That's what put this line on the z-axis. This point is halfway between that and that. So this point has x-coordinate, the average of those two numbers. So that point on that line, now that's the point r plus l over 2 minus near. Okay, so this is z equals negative near. Okay, that point, which is this point, should skew to that point, which is 0, negative near. Okay, but I can plug those 2 points into this equation and solve for s. And this is the s you get. Okay, so that's the skew factor in this formula. And that is the first formula in the code. That's the skew factor there. Okay, that's that skew factor. R plus L over 2 near. R plus L over 2 times near. See, there's the skew factor. See, there's the skew formula. That's this one up here. Okay, all right. So that picture derives this line of code in the x direction. And then for the y direction, you use top and bottom instead of left and right. You just use top and bottom instead of left and right. Okay, so this picture derives one of the lines of code. Now, what that does is it centers this view volume, but it still doesn't give it a 90-degree field of view. So the next step is to take step 2 is to take the centered view volume, like here, and scrunch it to be the standard. See, this light view volume is the standard view volume. See, there's the line x equals negative z, x equals z. That's the 90-degree field of view. This line has slope 45 degrees, and this line has slope 45 degrees. So the angle between them is 90 degrees. That's our standard view volume. We want to scrunch this view volume so it fits into there. Okay, so now we want a scaling transformation, not a skew transformation. Previously, we did a what's called a skew transformation. You're trying to shove that line over to there. So this line is being shoved over till it stands straight up. That's skewing. Now we're doing what's called scaling. What we're doing now is, whoops, where is my picture? Oh, did I close it? Oh, I must have accidentally closed it. I accidentally closed the picture. Okay. I want to take this view volume, which has an arbitrary field of view. This angle could be anything, and I want to shift that line to there while I shift this line to there. But that's a scrunching. That's not a shearing, or that's not a skew transformation. The skew transformation is kind of weird to think about. These two different transformations. Skew takes all these lines and moves them to the left. So this line will rotate over. This line will rotate over. This line will rotate over. Everything's rotating kind of to the left so that this one ends up on there. That's what we call a skew. The scaling, what we want to do now is rotate this one towards here and rotate this one towards here. And we do that by scrunching in the x direction by a s factor. So we take every x variable and scale it by a scaling factor S. In the other one, we were taking every X variable and adding a shift or a skew to it. So everything's skewed to the left a little bit, okay? Everything's skewed to the left a little bit, but things farther away skewed more. Things closer to the camera skewed left. In the scaling one, everything scales by the same amount. This one scales by the same amount that this one does, because now it's proportionate. So this one looks like it would scale less, but because it's smaller, it doesn't have to scale as much. This one's larger, it scales by the same amount this one does, but that gives you a bigger effect. It's like when the bank pays me 1% interest. It pays me less money than it pays Bill Gates, even though it's giving us both 1% interest, because he's got more money in the bank. That's what scaling factors do. Okay, it's proportionate. So this one's a larger X value, so it scales to a different, what looks like a different amount. What scales by a longer distance, but still scaling by the same amount. The other picture is a skew factor. That's different. This one skews more than this one does. This one skews a little. This one skews a lot. Here, this one scales the same amount as this one scales. They scale by the same amount because that's the difference between scaling and a skewing. Okay, so now what's the scaling factor? We go back to this point here. We know it scales to that point. This point, which is r minus L over 2 near. Oh, this point here is what this point here skewed to. So after you skew this point, see that's this little calculation here. What does that point skew to? This point skews to that point, r minus L over 2. This point, what does it skew to? It skews over to the left a little bit. It skews to this point, the symmetric one to that one, minus r minus L over 2. And the algebra is not hard. You can actually, the algebra for all this is, it takes more words. If you do the algebra, it's just, where is it? Oh, here it is. No. Oh, right here. The algebra is right in here. Once you know the scaling factor, you can compute where that's where it says that once you know the scaling factor, you can compute where this thing skews to and where this thing skews to. This one and this one skew to this point and that point. Okay, then this point scales to that point. So once you figured out where this point skewed to, then you want to follow up on where does it scale to. So you take this point and you scale it to, it says it right here, you're going to scale that point to that point. So then you can plug that into the scaling equation and compute the scaling factor. The scaling factor is 2 times near over divided by r minus L. And if you look at the code, that's here. There's the scaling factor. 2 times near divided by r minus L. Okay? 2 times near, well, let's see. 2 times near divided by r minus L is the scaling factor. And there's 2 times near times the x divided by r minus L. Okay? So this picture computes that line of code. One picture derives that line of code. One picture derives that line of code. And then the other line of code is just symmetric. You use top and bottom instead of right and left. Okay? And then so you can look at the picture. You can look at the words and the formulas. Here it's written more like it would be in a math book without any picture, just saying what the words are. And then here there's a picture that you can follow along with. And then there's the code. And that's it. All this stuff, those 4 lines of code do everything with aspect ratios and view volumes. Everything that we're doing which is amazing, that all of this is 4 lines of code. The ability to do all of that is just 4 lines of code. You transform the arbitrary view volume to the standard view volume. You transform the arbitrary view volume to the standard view volume using 4 lines of code. And then the standard view volume, you're back to your previous render. Once you're in the standard view volume, then you follow the standard view volume with the you follow the standard. Once you're transformed to the standard view volume, then you just project, clip, rasterize like before. Okay. See, so this part of the render doesn't change a bit. This is the elegance of the design. The design of a renderer is so that once you build one stage, the other stage should be decoupled from it. If I add a stage up here, that shouldn't affect anything that follows. If I've designed this well, when I add a new stage, I can plug it into the pipeline without having to modify any other stages in the pipeline. Later on, we'll put something in between these two stages. But when we put something between those two stages, we won't change this stage or that stage. Okay. Part of the goal is to design this stuff in a really nice way so that these are independent operations that have their own role, and that so putting this stage at the beginning of the pipeline doesn't affect anything that follows in the pipeline. Okay, so convert the arbitrary view volume to the standard view volume, and then just everything else is the same. 4 lines of code open up a whole new range of features to the renderer. When we ran the demos, you could see how much new stuff the renderer had. It's actually really amazing that, and that's one of the things I like about this stuff is how much one idea can have profound effect. Now that idea, now on the one hand, even though that idea is only 4 lines of code, it's not easy to wrap your mind around it. And it took people years to come up with these elegant ways to think about graphics. They didn't come up with this stuff like right off the top of their head on day one. This was done in the 60s and 70s. People thought and thought and thought and thought and thought, and they kept designing these things. And they finally came up with these really elegant strategies for chopping the pipeline into stages that are independent of each other, that fit together in an elegant way. No stage is really all that complicated. I mean, we saw that rasterizing and clipping can be messy, but not complicated. And like this stage is 4 lines of code, and yet it opens up a huge amount of features. Zooming and all kinds of things are now, you can see how I'm zooming in on that sphere, zooming in and out. Okay, the near plane's too. Okay, so you can see how I'm zooming in and out. Okay, so all kinds of things. Oh, here's the all this stuff. We haven't talked about matrices yet, but all this stuff is in that matrix. It will be eventually in that matrix. And the scaling factor, the numbers we've been computing are in that matrix. Okay, see, there's 2n r minus l. The 2n r minus l, oh, where's the picture? There's the 2n r minus l. See how it's in the upper left-hand corner of that matrix. 2n r minus l, 2n r minus l. So that scaling factor ended up being over here in a matrix. Then there's the scaling factor for the y-axis. Then the shearing factor, I think, is this guy over here. R plus L over 2 near. No, yeah, the scaling factor appears right there. The skew factor is kind of buried in here. It's almost this guy, but not quite. Okay, 2 times near. But then here's got f minus, yeah, there's more algebra. When you pack these numbers into the matrix, some of the numbers don't come out so elegant. The scaling factor is right there. The skew factor is a little bit buried in here. In some of these other, it's kind of spread out in these other components of the matrix. Later, we'll see how these, and that's why I don't want to use matrices yet. The matrices, this is one place where the matrices kind of obscure how elegant the ideas are. That's a pretty complicated matrix. And yet all we're doing is 2 simple formulas, the skew formula and the scaling formula. So we're only doing 2 simple formulas, skew, scale. So we need a scale factor and a skew factor. That's real simple. That's all that's really going on. Actually, when you stick it in a matrix, it gets a little bit more complicated. Okay. but it's just the way the matrix works. These numbers when they go into the matrix, one of them appears right there, and the other one gets kind of spread out over some other components. Okay, so a real simple idea gives you a profound new feature to the camera. And if you look in most graphics books, this is a whole chapter of the book. Yeah, because we spent a lot of time talking about. There's a lot to talk about. Aspect ratios just open up a whole lot of ideas, things you could play with. Distorting and chopping, and but it's all just 4 lines of code. Just these. It's amazing. Just these 4 lines of code give you all of that. And then there's this equivalent 4 lines of code for parallel. I haven't said anything about the parallel projection, but you do the same kind of thing for the parallel projection. Okay. All right. So we're that's pretty much it for view volumes. And that's almost it for camera. The last step for the camera is to make it move around. Notice that the camera sits put here. The camera never moves, and that's just like ours. Our camera does not move yet. This is not moving the camera. We're changing a feature of the camera. We're not moving the camera. And then after we learn more about matrices, then we can start moving the camera. It's impossible to move the camera without matrices. You can do this trick without matrices. The matrices actually make this thing a little bit more complicated, but you cannot move the camera without matrices. It's just way too, you can. Anything you can do with matrices, you can do without matrices, but it's a nightmare to move the camera without using matrices. You need that level of abstraction to be able to move the camera in any kind of a comprehensible way. So after we've done matrices for moving the object around, then we'll use matrices to move the camera around, which is a little bit harder than moving the object around. So first we use matrices to make the object move, and then we go and say, okay, now that we understand matrices better, we can see how to use it to make the camera move. Okay. All right. And okay, we ran out of time. Play around with the render. I'm going to try to get another homework assignment up soon. If they stop having meetings on campus, I'd have more time to write homework assignments. Okay, so time, there's just time keeps getting scrunched. Okay, so I'll try to have another homework assignment up there soon. In the meantime, play around with these renders, look at the code, and we'll start talking about and read the readings for matrices, and we'll start talking about matrices next week. Anybody have any question about anything that's come up lately? I haven't asked if there's any questions about anything yet. Okay. All right. Well, we're almost. Let's see. Next week we meet one time, right? A week from today is Thanksgiving, right? Isn't it? Thanksgiving's a week from today, right? Yeah. And so we'll meet on Tuesday next week. So we'll start the matrices next week on Tuesday. Okay. So have a nice weekend. Send me email if you have questions, or come to office hours. Bye.